Hello everyone. So in the last tutorial, I showed you guys how to import this robotic model into a URDF format from a SolidWorks CAD model using URDF exporter, and we made this URDF package for us. Now I went ahead and make a workspace in my virtual Ubuntu, which you can see here, and it's in the tutorial workspace. If you go into the source folder, you will see that I have this GP7 underscore robot package here. If we launch the file, because URDF exporter provides two launch files for Gazebo and Arvis, and if you first select and make this, which I have already done, and then close the workspace, I should probably go ahead and open it in code, Visual Studio Code. And we can see that under GP7 robot, there are meshes folder, launch file folder, concept folder, and under launch folder there are two launch files. One is the display, and which is basically Arvis display, and the second one is Gazebo. Now, if we, for example, start this launch file, Gazebo launch file, for example, we will see that it does not look exactly like the robot in SolidWorks model. In fact, it's a very bad looking robot because, and I'll show you why it's happening like this. If you see that it's sort of like this, and the problem with this is because URDF exporter exports the meshes with respect, exports these STL meshes, which you can see here, these STL meshes with respect to this global coordinate system instead of the local coordinate system or the frames that we assigned in the last video. So you need to export these STLs separately and replace them here in this folder. So you can visualize the model in Gazebo properly. To do that, what you need to do is basically you need to open each of the links separately in the assembly or part. Go into the save as settings in the file. Select STL. Select a folder. For example, in GP7, I make another folder. Mesh is new, and because this is the base link, I say base link under STL, and then you need to go into the options. So select output as meters instead of millimeters because ROS uses SI units as meters for distance. For resolutions, we are gonna tune down these resolutions for collision meshes, but currently it's okay if you select fine. Here in this, you need to select do not translate STL output data to positive space, and the second option, save all components as an assembly in a single file. Otherwise, because the assembly has a lot of different parts, so it will convert each part as an STL file. So we do not want that. We need only a single file for the whole assembly. So we are going to select this option. And for the output based coordinate system, it says default, which is basically the global coordinate system. So we need to select the one that we assign, which is this one. And this way we can export it. Click OK and save. Similarly, we have to do the same thing for all the other meshes. So I'll just stop the video and do it, and then unpause the video again. So I have went ahead and converted all 7 meshes into STL files according to their coordinate system. I've exported them according to their different coordinate system, and then I have placed them in my virtual Ubuntu, and you can see that it's in the new package here. So these are actually similar to these old meshes. The only difference is that these meshes are according to their local coordinate system instead of the SolidWorks global coordinate system. So instead now we need to change the location in the URDF file to, that points to these meshes instead of these meshes. So one easy way to do that is if we open our URDF file, we see that in each of the meshes under collision and visual. So if we type, yeah. So for example here, file name package, it finds this package, then meshes, and then links R4 STL. So instead of changing everywhere meshes to new meshes, what we can do is basically change the name of this folder to old meshes, and the new one we can just replace it with new meshes. Now, one more thing is, if you are still confused about why we did this stuff, so let me just show you how why it's important. So for example, if we see link C6 in the old meshes, and if you open with MeshLab, and if we do show axis of these under render, so where is this axis? The axis is actually really far away, that's why you cannot see it. It's basically, this is the axis and this is the part. So that's the problem. Now if we open the same mesh in the new meshes folder from the same, and if we sort of render the axis here, you can see that this axis is currently the one that we assigned in the SolidWorks. So this mesh is exported according to this local reference frame. So now we change these folder names. So the URDF now points to the new meshes instead of the old meshes. And if now we launch this file, we will see that it should work, and Gazebo should provide the exact same model as it was in the SolidWorks. It's going to take a little while because the SolidWorks CAD model was really detailed. They have actually pointed out every little detail in it, every screw in every corner. So there are a lot of a lot of vertices in this mesh when we exported it. So it takes a little bit time for Gazebo to respond these models. If you want, while this is spawning, so as you can see now, we have this model, but we do not have any controller or physics in it, and because the Gazebo is simulating gravity, that's why this is going to go down, and after some time it will collapse. So in the next video we will add controllers in it and show you how to add dynamics to properly simulate this robotic arm. There is one more thing that we need to do before finishing this video, and it's basically, normally what happens is that because these meshes are very detailed meshes, so when we'll be using MoveIt, there is collision checks. The collision checks are done by checking vertices of the meshes. So if you have very detailed meshes, then it takes a lot of time to do collision check in MoveIt. So it's a good idea to actually decrease the number of meshes decrease the number of vertices in your meshes. But the problem is, if you decrease the number of meshes, decrease the number of vertices, then the robot does not look good visually. So the common practice is basically you make two different folders in meshes. One is called visual, and it's here. Oh, sorry, I made it in a wrong menu under meshes. You make one folder for visual, and you copy paste all these files in it. So these are high vertices meshes, which will be rendered for only visual purposes, and for collision check, you will again copy paste these, but we will decrease the number of vertices in these meshes using MeshLab. So first we will actually close this, close MeshLab also. I'll show you how to do it for one file for collision, and then we'll do it, I'll pause the video and do it for other one. So I have copied the same number of meshes in two different folders. One is visual, one is collision. In collision, we will change the number of vertices using MeshLab for each mesh, and I will delete these here from here. So what we are going to do is open this with MeshLab. So we have this file, mesh, and if you look at the number of vertices, it's around 390,000 vertices. So suppose if it's colliding with another mesh which has 390,000, so it will be like this number of possibilities for collision check. So we need to tune it down basically and decrease the number of vertices in it. The way we do it in MeshLab is basically go under the filters and smoothing formation. Actually, it's remashing and simplification reconstruction. And in quadratic edge collapse definition, you see that there are total number of faces are these. So we need to decrease this. Basically, we don't need that many, so I'll just do 1500, and I'll have to preserve normal in topology so it does not deform very much. And if I apply it, you'll see that these well-defined mesh will not be that much well-defined after you decrease the number of faces and vertices in it. You can also reduce by percentage or by quality threshold, but I just like to do it by number of faces. It's going to take a little bit of time because it was a really detailed mesh. So once that, let me pause the video and unpause it again when it's done. So it's almost done, and now you see that this mesh does not look exactly similar to the one we had before. The problem is that we decrease the number of faces in it. For now it looks okay, but like if you are gonna, you can try it and you can reduce the number of faces to 3000 or 4000 depending on how good of a computer you have. I'll just keep it to 1500 and so I'll save this. I'll export this mesh as STL. Now, the problem with MeshLab is that it exports the STL format as XT format, not as a binary format. That's why the STL is a small instead of as capitalized or uppercase. So it's okay. So just export it, and I'm going to do the same thing for all the meshes here again. So I'll pause the video and do it, and then unpause it and show you how it's done. So I have exported all the meshes under the collision folder, and I've decreased the number of vertices and number of faces. So each file with the small .stl is basically the decreased STL file, and the one with the .stl, because it's a binary file which we exported from SolidWorks. So we need to delete it because we don't want that. And these are the 7 files because there were 7 lines. And now we have these files here. So under meshes we have 2 folders. For visuals we have the detail meshes, and for collision we have like tuned down meshes. So what we need to do is now go into the URDF file and point the visual tag into this folder, and for collision tag into these folders. So this is the URDF file that we have, and if we go from above, and like this is the geometry, under the geometry tag we have the mesh, and then under collision we have another mesh. So for geometry tag we have to write meshes and visuals, and for meshes for collision we have to write collision here. So it's the correct path, right? So it's GP7 meshes visual and basing, and it's GP7 meshes collision and basing. So for collision tag we need to write collision. We need to point it to the collision folder, and for visual tag we need to point it to the visual tag. So we need to do this for all 7 links. So I'll just go ahead and do it. Once again, I'm gonna pause the video. So I have gone ahead and completed, changed these folders and pointed them into the correct directory. So 1 minute, I did not change dot. For collision tags, I have to change this STL from capital to lower. So this, if I search collision, this is collision. So I'll just change it. This is STL. STL. So all collision tag have changed to STL, right? Yeah. So I'll just save this file and launch it again, and we'll see if we have an error. We'll see it here in the terminal. So we can testing it again, but it's not like necessary for now because we did not change any node. And we can go ahead and change this to the zero launch. And probably now we won't, like currently we'll see that though we change the meshes and we decrease the number of faces in meshes, but that's for only collision tag, not for the visual tag. So the Gazebo model will look like really good, but collision checking will not take a lot of time. So currently it's collapsed, but in the next video I'll show you how to add controllers in it and how to add actually position controllers in it. And we can find position commands, and it will follow that command for each joint. So thank you for watching. Subscribe to my channel if possible, like this video and share it if possible. Thank you. Have a good day. Bye.